Thanks, Robin. So this is based on joint work with Aram Harrow. Okay, so we're probably pretty far off from having a full-scale fault-tolerant quantum computer, but in the much more near term, we can hope to see noisy intermediate-scale quantum devices, which are far too limited to do things like factor huge numbers, but might nonetheless be capable of doing something interesting beyond the capabilities of classical computers. So to this end, many algorithms have been proposed as potential candidates that might be suitable for such devices. And a lot of them fall into sort of this broad framework of hybrid quantum classical algorithms. So in this setting, we have a classical computer interacting with a quantum device, and they're essentially working together to solve some optimization problem. So you can sort of imagine a cycle where the classical computer asks the quantum device to prepare some state and do some measurement, and the classical computer receives the measurement outcomes and then does some processing, and then decides what the next step should be. So first, I will sort of go over this framework, and I'll give a specific example of an application. So in the general setting, we typically assume that we can prepare some parameterized family of states associated with some variational ansatz. So here, psi naught, you should think of as some easy-to-prepare starting state, and then we essentially evolve it for p pulses. So here, pulse I is generated by some Hermitian operator A sub I and has an associated variational parameter T sub I. So any state in this family can be associated with some p-dimensional real-valued vector in parameter space. So the goal of these algorithms is typically to minimize some expectation value of some quantum observable H over the set of variational states. So you can think of H as effectively inducing a classical optimization problem in the parameter space. So typically in these algorithms, the quantum device is used to obtain estimates of this expectation value in low depth. So by low depth, I just mean in depth comparable to that needed to prepare the state T. So that's what the quantum device does. So then the classical computer gets this information, and it tries to solve some classical optimization problem. So in particular, it's trying to solve a stochastic optimization problem because it only has noisy access to the objective function f of t. Right, so an appropriate or common example is the variational quantum eigensolver. So in this setting, H would just encode some physical Hamiltonian. Maybe we want to learn something about the ground state. And there are various proposals in the literature on how to choose an ansatz appropriately such that it captures the properties of the ground state. So then if we solve the optimization problem, we find a minimizing parameter T star, which describes a minimal energy variational state. And if our ansatz was good, then we approximately learn the ground state energy based on f of t star. Okay, so remember this was the objective function. So how do we estimate this in low depth? So it's pretty simple. We can just do a Pauli expansion of H, so just write it as a linear combination of products of Pauli operators. And then each of these expectation values of Pauli operators can be estimated in low depth. So then we can just combine these estimates together according to the coefficients alpha in order to obtain some estimate of f of t. So if we want a very accurate estimate of f of t, we might have to do this very many times. And I've labeled this 0th order measurement strategy because this gives us information about the objective function itself as opposed to derivatives of the objective function. But it's also possible to do a similar procedure and obtain information directly about derivatives of the objective function, as has been pointed out in several papers in the last couple of years. So how do we do that? So recall that this is the definition of the variational state. So we can simply take a partial derivative of this expectation value with respect to some parameter j, and we obtain some expression like on the right-hand side. So here, the notation u1 colon j just means pulses 1 through j, and this just follows from the chain rule. And then I claim that we can estimate this imaginary part in low depth. So we can do that by just doing a Pauli expansion of these operators, and we end up with a linear combination of imaginary parts of these quantities where v, j, comma, a is unitary, and then we can estimate these imaginary parts in low depth. And I won't get into the circuit that does that, but if you're familiar with the circuit for the Hadamard test, it's just a simple modification of that. So then we can estimate these, combine according to the coefficients gamma, and this gives us estimate of this partial derivative. And I should point out that if you don't care about doing things in low depth, there's a better way to do this due to a recent algorithm of Guillen, Arunachalam, and Wiebe, which builds on Jordan's gradient measurement algorithm from 2005. Okay, so now I'll define what I mean by a kth order hybrid algorithm. So in the 0th order case, the quantum device just takes 0th order measurements, and then the classical computer does either some derivative-free optimization algorithm using these estimates of the objective function, or it could estimate the gradients of the objective function using the objective function estimates, and then it could run some derivative-based optimization. So similarly, in the first order case, the quantum device uses a first order measurement strategy, which gets information about partial derivatives of the objective function. And then the classical computer runs some derivative-based optimization algorithm. So we can generalize all of this to second and higher order measurements as well. Okay, so there were essentially two sorts of questions we were trying to answer. So one question was, how many measurements are sufficient to converge to a local optimum in one of these, in this setting? So the global problem is complicated and non-convex, but we can ask if we're in a vicinity of a local optimum, how many iterations do we need to converge, essentially? So this might be relevant in settings where we may want highly precise answers, maybe quantum chemistry. So we might spend a lot of time trying to converge in a vicinity of an optimum. So also, we were interested in whether first or higher order algorithms can actually obtain some provable improvement over 0th order algorithms. So for the first question, we obtain provable convergence guarantees that apply when the algorithm is within some convex vicinity of an optimum. So schematically, if you look at the picture at the top, this setting sort of applies when the algorithm is trying to optimize within this yellow region, for example. And this is mostly a matter of importing known convergence rates from the stochastic optimization literature and combining these convergence rates with different strategies for constructing estimates of the gradient. So I won't get into that too much, but for different algorithms, they work better with different strategies for constructing gradient estimators. So we're particularly focusing on stochastic gradient descent and also a generalization to non-Euclidean geometries called stochastic mirror descent. So we consider a version of that algorithm, which is appropriate for an L1 geometry. So this means that in parameter space, if we sort of measure distances according to the L1 norm, then we should use stochastic mirror descent. And if we measure distances with respect to the Euclidean norm, we should use stochastic gradient descent. And these methods yield different bounds. So then for the second question, we define and analyze a certain toy problem. And for this toy problem, we're able to show a provable speed up of a first order measurement strategy used together with stochastic gradient descent over any possible 0th order algorithm within a certain natural black box setting, which I'll talk about more later. So furthermore, we're able to show for this problem that this stochastic gradient descent strategy is actually optimal amongst all kth order algorithms. So now I'll say a little bit about the convergence guarantees. So this table is showing the number of measurements that are sufficient for convergence within some convex vicinity of an optimum. So I won't go over this table in detail, but I'll just point out a few features. So we consider, or we obtain upper bounds for both 0th order strategies and first order strategies based on gradient descent and mirror descent with an L1 setup. We also consider whether we have an additional promise on F that it is strongly convex with respect to the 1 norm or 2 norm. So these bounds depend on a lot of parameters. So some of them involve the size of the feasible set that we're optimizing in. The parameters E and gamma are related to the expansion coefficients that appear in the Pauli decompositions of the objective function and the gradient of the objective function. So we see for the 0th order case, it has relatively poor scaling with precision compared to the first order algorithms. Although I should point out that this is just the best known rigorous upper bound we have for the 0th order case, so it could be outperformed in practice. So then for the first order case, we see that if the function is additionally strongly convex, so that essentially, if you're not familiar with that, it essentially is a lower bound on the curvature of the objective function. We can attain 1 over epsilon convergence rates in this setting. So if in settings where we want a very precise answer, this could be pretty significant. And also, I'll point out that neither of the gradient descent or mirror descent bounds are strictly better than the other one. The better choice depends on what values these parameters take, which is connected to what the more natural underlying geometry for the optimization problem is. And actually, for the toy problem we study, the two bounds attain the same convergence rate up to a log factor. Okay, so now I'll talk about the toy problem we studied. So, so here is a definition of a Hamiltonian on n qubits, which is parameterized by this binary vector v. So every component of v is +1 or -1. And there's also this other small parameter delta. So this is actually an extremely simple Hamiltonian. It's one local. The xi and zi are just Pauli x and z operators. So to see what these parameters correspond to, here is a ground state of the Hamiltonian corresponding to a particular choice of v. So essentially, the ground state is just a product state on n qubits, where each qubit is polarized in the xz plane of the Bloch sphere, and the parameter delta controls how far away from a pi over 4 angle, the polarization vector is perturbed, and the binary vector v just controls for each qubit whether it's perturbed in the clockwise or counterclockwise direction. So for this family, we can ask how many measurements does a variational algorithm need to find a low energy state of h sub v for any choice of v. So in other words, say we have some variational algorithm that is good at optimizing all of these Hamiltonians, then what can we say about how many measurements it needs? So there may be something confusing here, which is that this model seems trivial, so it seems like we should be able to solve it by inspection without any measurements, and that's true, but in the more general case where we're optimizing more complicated Hamiltonians, this won't be the case anymore. So we want to somehow impose restrictions such that the classical algorithm can't just solve by inspection. So to deal with that, we introduce a particular black box model, and essentially the black box hides the specific details of the Hamiltonian h sub v. What this means for our bounds is that these bounds should be seen as sort of applying to general purpose variational algorithms, by which I mean ones where the classical outer loop doesn't use very detailed knowledge about the structure of the Hamiltonian to perform the optimization. So a few slides ago, when I listed a bunch of optimization algorithms, those would all fall into this general purpose category. Okay, so let A be any 0th order variational algorithm that satisfies the following properties. So first of all, we want it to be good at optimizing all of these Hamiltonians. So for any Hamiltonian in this family that's realized, it should output a description of a state such that the expected energy of that state is within epsilon of the true ground state energy. And as we said before, it shouldn't solve by inspection. We also impose a restriction that the algorithm only prepares states that are close to the optimum in some sense. So we don't allow it to prepare states that are far away from the possible set of optima in some sense, which I'm not making precise. So we can show that under these conditions, we need at least n cubed over epsilon squared measurements for an algorithm to satisfy these properties within the black box model. And similarly, we can ask about kth order. So in this case, we can show that n squared over epsilon measurements are both necessary and sufficient. And furthermore, the upper bound can be attained with only first order measurements. So for this particular model, second and higher order measurements don't bias anything. Okay, so now I'll briefly sketch the proof idea for the lower bounds. So we have this family of Hamiltonians that we want our algorithm to optimize. So we actually start by restricting the problem to a subset of these Hamiltonians, which is a good packing in some sense. So by that I mean we want the subset M to contain as many elements as possible, but we also want it to satisfy this property that essentially if some state is a low energy state with respect to some Hamiltonian in the family, so it's a pretty good solution in that sense, then that state should be high energy with respect to any other Hamiltonian in that family. So a state that's good for one should be bad for the others, essentially. And right, so we actually prove our lower bound with respect to this family. And the reason why this is useful is because if we optimize any Hamiltonian in this family to high precision with our algorithm, because of this packing property, that will imply that we can actually learn the Hamiltonian that was realized. But remember, this Hamiltonian is encoded in a black box. The algorithm doesn't have direct knowledge of it, so learning it is non-trivial. So then we use information theoretic methods to lower bound the number of measurements needed to learn the Hamiltonian in this set that's realized. Okay, so that was the lower bound. So I said that the upper bound could be achieved with a first order algorithm. So to do that, we can start by making a good choice of variational ansatz. So in particular, we can choose a product state on n qubits, where each qubit is polarized in the xz plane of the Bloch sphere, and we can choose our ansatz such that we have n variational parameters, and for example, parameter 1 just controls the angle of rotation of the qubit 1 away from the pi/4 angle. So if you remember what the ground states of these Hamiltonians looked like, it should make sense why this is a natural choice of ansatz. And indeed, if we make this choice of ansatz, then the objective functions that are induced are strongly convex. So they have essentially nice curvature properties. And this is good for optimization. So stochastic gradient descent can take advantage of this. And using first order measurements and running stochastic gradient descent on top of these gives us the desired upper bound. And I'll also point out that if we decide to use L1 geometry and use stochastic mirror descent, we only do a factor of log n worse. So they're fairly comparable. So there's a lot of directions for possible future work. So first of all, this was all very theoretical, and it would be important to understand how these results relate to what happens in practice. So in particular, these upper bounds could be loose in practice, and also our upper bounds on convergence relied on having this trusted region, essentially, where the algorithm has a region where it believes contains a local optimum, and it believes that the function is well behaved in this. So what happens in practice if we don't have a region like this? Can we construct one, or what should we do if we can't? So also, I didn't say anything about noise. So clearly that is not reasonable in practice. So it would be important to understand how all of this behaves in the noisy setting. Also, second order measurements didn't improve our example at all, but more generally they might. So that's another interesting question. Also, we had these different bounds that performed better in some geometry versus another geometry. So it would be interesting to understand what geometry is more natural for these variational algorithms in practice. And relatedly, in this table of parameters for the upper bounds, what sort of values do these parameters take on in practice? So finally, there was a recent paper by the Google group that studied the situation where you're in the regime where the variational ansatz essentially looks random. And when you're in this setting, they show that the optimization landscape looks extremely flat because of some concentration of measure effects. And this situation can sort of be seen as the opposite as that studied in our toy model, because in our toy model, we made a very wise choice of ansatz for the problem at hand. And because of that good choice, we were able to obtain objective functions that were very well behaved. So it would be interesting to understand which of these scenarios is sort of the more realistic one in practical applications. Thank you.
Thank you very much. The floor is open for questions.
Good talk, thanks. I had a quick question, which was on the gradient-based kind of bounds that you had. I noticed that for some, like in the strongly convex case, it seemed like the complexity of reaching the minimum scaled better than estimating the energy of a single point at the minimum. So I was kind of curious about your thoughts on that, and also how you think about terminating the algorithm when that's the case. Thanks.
Yeah, that's an interesting point. So, so these 1 over epsilon results for the strongly convex case. So the algorithm in these settings could potentially find a parameter that is an epsilon approximate optimum faster than it could actually estimate the objective function to precision epsilon. I'm essentially not sure exactly what to make of that. So for example, like for quantum chemistry applications, we're usually interested in estimating the energy. But yeah, I'm interested in whether these 1 over epsilon rates could somehow be exploited. Maybe you could do something interesting, or maybe you could somehow take advantage of finding these parameters faster than you could estimating the energy. So my understanding is that often in quantum chemistry applications, we're sort of more interested in energy differences in some sense. So this kind of feels like gradients. So it would be, it's an interesting question whether these rates could be helpful in that setting, but I'm not sure.
Thanks.
Hi. I wanted to ask what class of functions and over what class of convex sets are these bounds valid for?
What class of convex functions you said?
That's right.
So these bounds just apply for general convex function. Like these are very general bounds. So in this row, we're really only assuming that the objective function is convex. And then, in this row, we just have the additional assumption that it's also strongly convex.
And the set, what is the kind of set over which this function is defined?
So the set, so essentially these bounds are applicable when the variational algorithm somehow has like a trusted region in some sense that or you could think of it as a promise problem where the variational algorithm is given some convex set such that the objective function is convex or strongly convex on that set. So the only assumptions we make about the convexity of the feasible, the only assumptions we make on the feasible set are that it is convex. And then we also these R1 and R2 parameters are where like the radius of that set comes into play. But we don't make any more specific assumptions other than that.
So even ignoring the noise in the evaluations and the gradients, the free parameters are you're parameterizing a Hamiltonian, not a circuit, and that the complexity result wouldn't translate to each other, right?
Sorry, I didn't quite hear.
So you have a set of free parameters where you're minimizing the energy of the Hamiltonian with respect to those.
Right.
But in variational methods, you have these free parameters that parameterize a circuit. So you have a unitary instead of a Hamiltonian.
You're talking about like these T parameters?
Yeah. So if the parameters are, for example, angles of rotation, that wouldn't be the same as assuming you have a Hamiltonian that is written in terms of those three parameters.
Right, I guess so we consider a setting where the Hamiltonian is fixed and we're varying over variational states. I think I might be a little bit confused, sorry.
Talk about it.
So are there any further questions? All right, then let's thank John again.